Hello. Okay. Last time we left off, which was about a week ago, we had done some work on integration. We have some simple sort of utility results here for the first section. So we've got integration is essentially defined using the substitution rule. Which is sort of as you would expect, and then it's linear on each over a real path like 0, 1. It's linear on each projection. With that, so we have this general sort of rule. So we've merged our integration is sort of an extension of complex integration. So any of the results that we find for these will also apply to complex integration. Of course, we're not really going to find anything new for complex integrals, but many of the properties will be shared. We have, let's see, sort of the standard results. Integration is additive. It's also linear. And we can pull out constants from an integral. This is important because we know that sometimes when a constant is not a unit, this can be kind of finicky, but we've sort of gone through the steps and shown that actually it's fine, and that for any constant we can just pull it out. And the integral will exist either way, one way or the other. We've also shown, we have sort of a variant of dominated convergence theorem here. So integration is roughly continuous in the sense of these conditions. If we have a bunch of integrable functions and they're bounded across both, across every function is bounded uniformly across all x, and they converge pointwise to an integrable function, then we can pull in the limit. We also have these other two theorems. So these last two theorems that we worked on were if we have a locally convex domain without isolated points and a continuous function f, then the indefinite integral functions for f, if it has any, are also antiderivatives. That's one of the things that we found out. We also sort of have the converse of that. It's a little bit stronger. The converse statement that we found was if we have any antiderivative for a function f, then for any of the curves that f is integrable over, that antiderivative also acts like an indefinite integral function. So it has this indefinite integral property, which essentially means that, for example, if f is integrable in general, so it's integrable over every contour, sigma, in that case, then any of its antiderivatives are just indefinite integral functions, and that means it has a path-independent integral. So those were the last two theorems we sort of left off on. So long as our domain is sort of nice, and this idea of using locally convex domains, we'll use that a lot. That'll be a recurrent theme. Yes, so locally, just to be clear, locally convex basically just means that in every for every point is contained in a convex neighborhood, subset of that set. So that is actually sort of what we use here. Is we say since S, is locally convex, if we take some point in that set, then we can find a convex neighborhood for that point. That's a subset of S. So we'll use this property a lot. This local convexity is really useful. So our next plan is we're going to get more into how integration relates to differentiability. So here we've got that integration is sort of the opposite. In some cases, integration is the opposite operation for differentiation. But we're going to do, for these next few theorems, I sort of laid out the theorem statements and drawn up some proof sketches. But we'll work through these theorems, and ultimately, these theorems will build up to the point where if we have sort of, a nice domain and a differentiable function, then any differentiable function also has an indefinite integral. This is really useful, actually. because essentially what it says is that if we have a differentiable function, then it has infinitely many antiderivatives. We can go sort of in the reverse direction of differentiation as many times as we want. That's super useful for us. We don't have this result for non-differentiable functions. I think the general result is impossible for non-differentiable functions, and the reason is our set A is multidimensional, so it's not as simple as just real numbers. And I think even in the case of complex numbers, that ends up being the case. There are lots of integrable functions, meaning continuous functions, which are not in just in the context of complex numbers. There's lots of integrable functions, continuous functions, which are not actually differentiable. They're not complex or differentiable. So we shouldn't expect to be able to remove this differentiability condition. But having this theorem apply to differentiable functions is really nice. This is going to help us a lot, especially in the next coming sections that we'll write. So the way we work up to this is we're going to sort of do it in stages, and I can describe the overview sort of proof sketch that we're thinking on. So the first theorem that we'll prove in pursuit of this ultimate goal is we'll prove that if we have a convex domain for a differentiable function, then the integral of this function f, this differentiable function, across a triangular path is 0. So essentially, ultimately what we want to work to find an indefinite integral function, we're going to show that our function has a vanishing integral on any loop. And so we're going to start by, instead of starting with the domain as being locally convex and simply connected, we'll just start with it being just normally convex, which is a much stronger condition. We'll start with our set being convex, and we'll prove it for triangular paths. Once we have it true for triangular paths in convex domains, using sort of a quick induction, we're going to be able to prove it for polygonal paths. So a polygonal path is just concatenation of a whole bunch of linear paths, and if those paths end up in a loop, then we'll show that the integral is 0. That's actually pretty straightforward. You just sort of do it you just use the triangle case in an induction, and this works because the domain is convex. Once you have that for all polygonal paths, to prove it in a convex domain for any path, so to find an indefinite integral function, we can just approximate any contour, any loop. We can just approximate that loop using polygonal paths, and then we'll prove that those approximations have the integral tend to what we need it to. And so by approximating any given loop with polygonal paths and the path independence over triangular paths, that should give us that a differentiable function in a convex set has a path independent integral. So that's sort of the first two steps. The last step is to upgrade all the way to locally convex. This one's a little harder. Each one of these has different sort of methods to approach it. But the locally convex will be exploiting this convex case. So we'll break down this domain into a convex base. So we'll find a bunch of convex open sets that sort of cover this set. And given some loop that we're integrating over, since this set is simply connected, we'll find a homotopy, and then we'll use that homotopy. Essentially, we'll use that homotopy to show that we can use within any of these convex, base sets. We'll show that we can jump between the different sort of rings, different distances along this homotopy, to show that the integral vanishes. That's sort of the broad overview, the broad strokes. But we'll just start up here at the top. So the proof sketch for this one, for triangular paths, is going to be rather interesting. So let me give us some space here. So essentially what we want to do for this one is we're going to follow a similar technique as the Cauchy-Goursat theorem, which is a complex analysis theorem. This proof it sort of works by you know, we start with a triangle and we cut that triangle up into different pieces. As we sort of cut it up into progressively smaller pieces, we'll pick whichever integral has, you know, the largest magnitude or the largest value, and we'll find a limit point for all these triangles. And then we'll use differentiability to show that, in fact, all these triangles had to have a zero integral. So we'll try to work it like that. So we'll just sort of start right out. So before we get to this, we're actually going to need a lemma. So what we need actually is we need to be able to approximate integrals themselves to put upper bounds on an entire integral. So the way we're going to do that is we're going to define a length function for contours. So let's see. So let sigma be a contour, then we can define a length function. Yeah, let's actually put that in front. We can define a length function for contours using integration and the a function. So sort of the trick behind defining the length here is that we're actually going to define, instead of finding a real number to measure its length, to sort of assign a length value to it, we're actually going to find a sequence of real numbers, so a point in our a sub r, as measuring its length. And the way that we're essentially going to do that is instead of measuring sort of length using the Euclidean distance, we're actually just going to measure the variation on any projection. So we'll define this as the length of sigma is defined as equaling the integral from 0 to 1 of sigma prime of t dt. Actually, we want this to be a of sigma prime of t dt. We could also write this, if we wanted, as sort of like this. This is sort of informal notation. Essentially, we want to, in order to calculate the length, we want to calculate the absolute variation. So this would be the integral on its whole path of just sigma prime of t. Yes, so what we're going to do with this length function is we'll be able to bound any integral using this. So we'll say let f be integrable over sigma and such that we'll say a of f is bounded by some, let's put some bound b in a sub real. See how that looks. Be integrable over sigma such that actually we can say integrable and bounded over sigma by, that's better, okay. And then the theorem statement is, hello. So the statement is that this integral, if we take, if we apply the a function, the absolute value to this will be bounded by, we'll have integral on 0, 1. This will be, let's see, the length of sigma times b, I think. Seems about right. Yes, I think that's correct. So the proof for this is kind of straightforward. So we'll say, so we'll do this. We'll prove this using the triangle inequality for complex integrals. So we'll say, let's see, we'll start with the beginning. So we have integral on sigma of f of x dx. This is just the integral on 0, 1 of f of sigma t, sigma prime t dt. And we can also rewrite this as, actually we'll just go straight from the definition. This is the sum on n in natural, actually we'll do k, because I usually do k for indices, e sub k times this integral 0 to 1 of p sub k f of sigma t, sigma prime t dt. Yes, okay, so we have this term, and then when we apply the a function, we'll have this. And ultimately this will just be the absolute value. So we'll say, okay, so we want to do a bound, so we'll say f of sigma t, sigma prime t, a of that is preceding a of f of sigma t, sigma prime t, and this should be and then this is bounded by okay, there we go. So this is our first step. So we want to take this integrand. So we'll have f of sigma of t, sigma prime t. If we apply the a function from submultiplicativity, we sort of distribute this a to the different functions. And then f is bounded over sigma by this b. So we can just replace this whole term with b. So this will be bounded like this. So since f is bounded Okay, so that's the first step. So we sort of done sort of the primary approximation. So this is the important part. Then for each projection, we'll bound, so we want to end up here. So we'll say, take the piece of k projection here. We want to do, this will sort of jump us right over to this. See how that looks? Okay, that's good. And then we also know, just by triangle inequality for complex integrals, we can pull this absolute value in. I'm going to have to do an alignment environment here in a second. And this whole term is bounded by pk of, instead of this, we'll do b, and then we'll do a of sigma t. And I think this one should have gone inside the dt in the previous line. Okay, so let's put that in a line. And I'll break that off, I think, perhaps right there. We'll figure it out as we go. But this is the basic strategy, essentially. We just want to use this sort of property. And then we'll just use the triangle inequality for integrals, for complex integration. So we bound the pk projections, we have this is this, so we can sort of flesh this out a little more. We can say, instead of jumping from this pk of a right over to this absolute value of this thing, we can sort of stretch this out a little to make it a bit more clear, just show some of the intermediary steps. So instead of doing pk of a of this integral, we'll do the absolute value of the pk projection. There we go. And then on this inside part, we can switch to 0, 1, s sigma t, sigma prime of t dt. And then when we advance, we should have integral pk sigma prime. Let's see if we can figure out how to do the spacing on this. We might have to do another line break. Okay, so we're going to take this integral, this absolute value integral, which is sort of the integral we want to bound up here. We're going to evaluate its pk projection. This is just equal to, by definition of the a function, the projection of the a function is just the absolute value of the projection. So we have this absolute value of this projection of this integral. Because we've now switched this inner integral, we've now switched it to this substitution rule, we can pull in this piece of k, because we have a complex domain, so we can pull in this piece of k, this pk projection, and then using the triangle inequality for complex integrals, this can be bounded right here by just pulling in this absolute value. But then this PK projection, we've already found out that this absolute value of this expression, which is in here, this is just bounded by this. We could probably make that a bit more clear. For example, instead of doing absolute value of PK in here, we could flip these around and do PK of the A function. Or we could say, no, this is fine. Yeah, we'll keep it like this. So this is absolute value PK, and then we have this term here. So yeah, well, actually we will do this part. So this is just this. We'll swap around these terms. That seems good, I think. We will separate these onto more lines, though. So let's see. We'll add a new line here. And then I will add a new line here. That looks okay. So what we've done is we've established this part first. Then we've said for each index k, we can do this whole approximation, and then we can sort of be a little verbose about this. So we can say, so the first line is just sort of standard. We're replacing this a function with the absolute value, pulling, doing the substitution. Then we're pulling in this pk. All of that is normal. The second line is justified by triangle inequality for complex integrals, or I guess I could just say integrals over real paths. And the third line is justified. Okay, let's write that. So okay, yes. So the second line is justified from triangle inequality for complex integration. Third line is justified by monotonicity for integration over real paths. And then we could say oh right, let's actually pull out this pk at the end. That should actually be nice. So we'll plot this pk projection. This will be this integral pk this should be outside, I think. Oh, I have mismatched parentheses. We need one right there. Let me make sure all these line up. So 1, 2, 3, 4, 1, 2. Okay, this one's good. This one is good. This one needs an extra one. I think that should be right there. Okay, that matches up. Although we also have this extra absolute value bar that isn't matched up somewhere. That's because it doesn't belong there. believe it should be like this. Okay, yeah, that checks out. And this is, so this is this. This is bounded by this from this term. And then we just sort of expand this out. This is pk of that, which is, we can pull out that b from the integral. And then this is just p sub k of b length of sigma. Let's see how that looks. Okay, that's good. Yes, so the second line is justified by triangle inequality for integration over real paths. Third line is justified by monotonicity of integration. And then on the third line, on the fourth line, we're just sort of expanding out this expression to show, you know, if we pull out this projection and then we pull out this constant, this is just this. We can actually probably shorten that. We don't need all of these. We could probably put that up like that. I think that would be fine. Nice. Okay, that's very good. So because we have inequality on every projection, theorem is proven, and we will restate the claim, which is a of the integral 1 sigma of f of x dx is bounded by b times the length of sigma. There we go. So that's nice. So this lets us, essentially what we've shown is that we can bound any integral. It can be bounded by the length of the path multiplied by some bounding constant for this function. This is pretty useful because right here we're just using this is a product, in fact, between b and the length, a Dirichlet product. So this is very interesting for us. It's very nice. But yes, so this is sort of our inequality. Another thing that helps us is, for example, if our function is very simple, as our path gets smaller, that it decreases linearly with the length. If our function is just sort of staying one constant thing, or if our function is decreasing, the integral also decreases linearly with its bound, with its upper bound. So this is a pretty useful approximation, despite the fact that this length is, it's not a real number. It's this weird, sort of absolute value of the, absolute variation on each projection. This is still pretty useful for us. So we can use that to do a lot of things. Okay, so next we want to sort of set up this, so this theorem here. So this is the first part that we want to do. The next part we want to do is we want to set up a method for concatenating paths, so you want to probably make that a little explicit. So this will be kind of straightforward. So we'll say given two contours sigma and gamma such that sigma of 1 is equal to gamma of 0, this is probably not super necessary, but it'll be nice. So it'll be nice to have this. So we'll have so we'll have this as sort of a piecewise function. So we'll have sigma of 2t if t is less than 1/2. Otherwise, we'll have gamma of 2t minus 1 when t is greater than or equal to 1/2. So essentially, if the endpoint of gamma is the starting point of, if the endpoint of sigma is the starting point of gamma, we can concatenate them, sigma into gamma, using this definition. So we get this new contour. It traces out the path of sigma for the sort of the first segment, and then it traces out the path for gamma on the second segment. So for t greater than or equal to 1/2. If we want, we could probably make this a little more explicit. So we could say t is in, 0 to 1/2. And then the second case is t is in 1/2 to 1. Okay, so what do I want to say? So concatenation has so we want to sort of identify some of the interesting properties that concatenation has. So we'll consider three contours to state our properties. Okay, so the properties we want to identify is the first one we want to show is in terms of integration, concatenation is sort of linear. So if we do this integral sigma 1 connected to sigma 2, this is just the integral of sigma 1 plus this integral over sigma 2. So if you concatenate the paths, it's the same as just summing the two integrals. We also want to identify that concatenation is essentially associative. So if we integrate across, we'll do something like that. So if we, it doesn't matter, essentially what we're saying is if we concatenate them and integrate over that path, it's the same as just summing the integrals. And if we concatenate them in different orders, it doesn't really matter to the integral in the integration, it's the same either way. We also want to identify this length function actually. Sort of additive with these operations, and we can actually put that first. Maybe that'll be a bit more clear. Oh, whoops. Okay. So this concatenation operation will be useful for this next proof. Let's line these all up so that this is nice and clean. Okay, that's a little better. Okay, I think this is maybe all we needed. There's one other thing we wanted. This length function. Let me think. We can do a length for a linear path. That one's kind of straightforward. I want to identify that, I guess. Maybe it's fine, I guess, actually. Okay, anyway, so we've got sort of these properties. So length is additive when you do concatenation. That seems sort of straightforward. If you concatenate the paths, that's the same as summing the integrals. And concatenation it's parametrization independent. So so concatenation is effectively associative in terms of integration. Okay, I think that's maybe all we need to set up this next theorem. So, okay, we'll just try to get into it, and we'll add more notes if we need them. Okay, it's taking a minute. Okay, there we go. Okay, so to start off this proof, we're going to want to consider, so a triangular path. We'll call this delta, and we'll say that this path is going between these A, B, and C. So take A, B, and C in S and consider the triangular path, and so we just concatenate these line segments. By contradiction, suppose that this integral across delta of f is non-zero. So we'll do this by contradiction. So we'll assume it's non-zero. This is really not complying today. Okay, so by contradiction, we'll assume that this integral on this triangle path is non-zero. Then what we'll do is we'll say, let's see, let's call this actually delta naught, delta zero. So given some triangle delta n over which this is the case, we form a smaller triangle. We'll do this delta n plus 1 over which let's see, okay, actually we'll do let k in, so we'll pick an index find an index k natural. Oh, actually maybe that'll be a faster way to do this. Let me think on that. We may not even need to do this. I'll leave this text here, and I'll try to work that out real quick. So it may be possible, actually, to utilize the ordinary Cauchy-Grosset theorem to prove that this is zero. I'm not sure if that will work, but we're gonna see. So I want us to take this integral on delta f of x dx, and I want to rewrite this as let me think. Somehow we want to put this on a plane, if possible. We can say integrate on 0 to 1 f of delta x t, actually, delta prime t dt. Let me think on that. Let me just look at that for a second. So I think what I want to try to say let's do a projection. Piece of k. I think actually this might work. pull in this projection, right, like this and that. And we'll say this is we'll do our summation. AP equals K. We have piece of A, piece of A of F. And then we have P sub B of delta prime. And maybe we can pull this out. Okay, so what we know is maybe we do need the summation. So what I want to try to do is to show I want to try to show that actually this whole summation is I want to show that, so the ordinary Cauchy-Grosset theorem, essentially, it proves this property, but in case the domain is complex. So if it's complex differentiable, then it has a vanishing integral over any triangular path. I want to try to recycle that. So I want to try to show that, I'm not sure if this will work yet. I want to try to show that, I know this theorem works, but I don't know if this approach will work. I want to try to show that somehow this integral is equivalent to some integral on a of a differentiable function on a triangular path. That's kind of what I want to show. I'm not actually sure if that'll work. What we can try to do is we can say, well, this p sub b of delta prime is technically the derivative of a complex triangular path. So that works because p sub b of, so it's piecewise. So delta prime is piecewise. It has three pieces, each of which are constant. So p sub b, the b projection of delta prime, also has that property. It's a piecewise function composed of three constant pieces. So this should be, at the very least, it's a polygonal, it's the derivative of a polygonal path. But then we can just integrate this. If we do integrate 0, 1, p sub b, and we do delta prime of t dt, we can pull out this projection. So something like this. So this B projection of delta prime, if we integrate this from 0 to 1, this will be, actually, p sub b of delta prime is just the derivative of p sub b of delta. So this is actually much easier. And we know that since delta is a triangular path, its projections are also triangular paths. So we could attempt to do it that way. So this is this. So this is a triangular path, at least. What we can try to do, in order to turn this into what we want it to be, we can try to relate this to this triangle. So we can say, let's do delta 2 is just p sub b of delta. So we sort of project delta down. So you can try that. If we do this, we can say p sub b of delta prime, this is just delta sub b prime. So we can rewrite each of these terms. Let's see, where are they? Each of these integrals. This is this p sub b delta prime. This is actually delta sub b prime of t. Now all we need to do is reverse this sort of thing. So what we can do is we can say have oh yeah, this will definitely work. Okay, so we can do delta sub b and then delta sub b inverse function. And then this is just the integral on delta sub b of this projection p sub a f of delta b inverse. X dx. Okay, this will definitely work. I'm excited. Okay, so okay, so the Cauchy-Goursat theorem is a theorem in complex analysis. It says that If we have some domain omega, which is a subset of the complex numbers, if that set is convex, and we have a function g mapping omega to complex numbers, which is complex differentiable, then g has a vanishing integral on any triangular path. Actually, technically we don't really need the Cauchy-Courset theorem itself. This follows from lots of other theorems about complex integration being path independent. But we can just sort of leave it like this. G is complex differentiable, then it has a vanishing integral on any triangular path. So what we can do is, so collect any indices A, B, in naturals. And what we're going to do is we'll consider sort of this technique that we've done. So, okay, so for each index A in natural, let delta sub A be equal to, actually, be equal to P sub A composed with delta sub, just delta, actually. Okay, so that's that. Now I want to say okay, so this is good. Okay, so we've got this projection of this integral, do the substitution rule, pull the p sub k in, do out the summation, and then pull the summation out. And we can also, actually we'll move these other terms. Okay, so we've done all these summations, so we will show can also rearrange these if we wanted. I think this is fine. Okay, so okay. Okay, so we're saying let delta be a triangular path in our convex domain. Select any index k, and we're considering the k projection of this integral on this triangular path. If we work this out, we'll get, this is just the k projection, so we do the substitution rule here. We pull in this projection, we use the definition of Dirichlet product, and then we pull out this summation term to the front. Once we've done this, we have, so this integral 0, 1 of these projections. So what we want to do is we're going to show that this is the derivative of a complex triangular path, and this is going to be a function which is complex differentiable on that path. So to do that, so we'll say, we'll show that for each AB the above integral vanishes, so we'll say for each index B, since the P sub B projection is linear. Okay, so now that we've laid out this part, so we're going to show that for each A and B that this integration vanishes. So for each index B, we'll consider this triangle. So delta B is just delta projected down to the B dimension. Since delta is a triangle, this projection will also be a triangle, especially since projection is linear. So delta sub B is a triangular complex path. Also, since P sub B is linear, it commutes with the real derivative, so actually I should say it's linear and continuous. As it's linear and continuous, it commutes with the real derivative. Actually, it commutes with the complex derivative, but we might not need that just yet. So it commutes with the real derivative. So the projection of delta prime is just that, the projection's derivative. So if we have delta prime and we project that to the b direction, this is just the delta b prime. So this lets us rewrite our integral as, so we have this term here. Oops. So this term on the end, this is just, instead of P sub B, so P sub B delta B. Okay. We also want to show, so what we want to do is we want to show that this inner term is going to be complex differentiable. We'll figure out how we do that soon. What we can do, though, let's see. So if we're going to show that this is complex differentiable, eventually what we'll have to prove, so we have P sub A, F of what is this term actually? Hold on, let me clean up here. Don't need that. don't need this. And this is just that. Okay. We also don't need this. We'll leave this here in case this doesn't pan out. Okay, so this lets us rewrite our integral like this. So we'll say let's see, so can we actually do an inverse? Sort of, maybe. If we do want to do a derivative here, so let's see, what is, because eventually we want to show that this is equal to this. Delta B is a complex path, and we want to show that this is, so we'll assume for a moment that delta B inverse exists. If it doesn't exist, then actually our path is sort of degenerate, I think. If the inverse doesn't exist, then it sort of overlaps itself on that index. In that case, delta B prime is, actually delta B goes, oh gosh, maybe this won't work. If we were to do a derivative, so on this would be, this derivative pulls through, we get this, and this would be f prime times the derivative of this whole thing which is delta prime times the derivative of this whole thing, which is delta B inverse prime of x. Double superscript, doesn't like that. I think probably the problem is that this inverse function won't necessarily be differentiable, which is unfortunate. So no, actually this method, oh wait, no. Delta B is a complex path. Okay, actually this is maybe fine. Let's pull this over there. That's where that belongs. Or, alternatively, actually, I think I've gone about this in the wrong way. We can instead say, right here, this is weird, treat, instead of doing delta B, actually not here, up here, instead of doing delta B, we can actually pull out this B projection over the A projection. P sub A is a complex number, P sub B is linear, so that pulls out there, and that'll pull out all the way through there. That actually might work. Okay. And then we get, this whole integral is delta x dx. Oh my gosh. Okay, it does work. It does work. Okay, so what we have is, so we do this projection, we do substitution rule, we pull the projection in, do definition of Dirichlet convolution, pull the summation out, pull this P sub B over this projection, this P sub A projection. And then this is just the P sub B projection of this expression. That is great. That actually works. Wow, okay. Okay, I wasn't expecting that. And then I think we just have to show that P sub A of F is complex differentiable. Actually, that doesn't make sense. We will figure this out, though. This is definitely really close to what we need. I think what we can say is P sub A of F should be complex differentiable, which means we can give it a power series representation. That could be one way to do it. And that power series representation has an antiderivative, and we can just use that as an extension naturally. That might actually work. That's definitely not what I thought I was going to do in this proof. Of the actually, to be honest, this approach is extremely powerful. We don't even need to limit ourselves to No, yeah, we don't need to limit ourselves to triangular paths. It's enough to just have this be convex, actually. It's enough to just have this be convex. And I think we may need, instead of convex, oh gosh, let me think. Because piece of A of F is defined on this S domain. It's complex valued, but defined over this domain here. Maybe we can't do this straight away. This is a really interesting way to look at it, though. To pull this projection over the other one. That's definitely not what I thought I was going to end up doing. Okay, yeah, I think ultimately we're going to have to go back to the original method. That's okay, though. This was informative. Okay, so... Okay, so take our ABC, triangular path, suppose that this is non-zero, find an index k. We'll say actually the least index k, for which we have PK projection non-zero. Okay, so essentially what we want to do, so for this proof, so we're going to try to find a second smaller triangle. So the usual a proof for Cauchy-Goursat essentially uses this sort of method with these triangles. So you start with your first triangle, and then you cut it up sort of into this sort of fashion. So you take these midpoints and you draw these lines. If you add up the integrals on all 4 of these sub-triangles, where you take the middle triangle in the reverse orientation, I think. Let me this way and this way. Yes, the middle triangle in the reverse orientation. One of these 4 triangles, essentially, one of these 4 triangles has to be at least as large as a fourth of the original integral. And you just you select that triangle and then you repeat the process. So if it was this lower right triangle, you'd split it up again, find another subtriangle. Repeating this process ad infinitum gives you this infinite series of triangles, which tends to a point. And then you just use differentiability to show that it has to decay faster than this powers of 4 that you're using. So that's sort of the approach that we're going to do. So we'll say so I suppose this integral is non-zero, v syntax k, for which this is non-zero. So we'll do, to maximize this integral, so smaller triangle, we'll say delta 2 subset equal to the convex hull of A and B, C, for which the length of delta 2 is equal to, it should be I want to say this is half, right? Length of delta 2 is 1/2 the length of delta but the integral along, actually we can say the length is half of delta and the diameter is, I think this will also be a half of the diameter of delta, but the integral on delta 2 of f of x dx, if we do this p sub k projection, and we do the absolute value, this absolute value of the projection, this is greater than or equal to a fourth. Yes, a fourth of the original integral. So, ABC, consider this triangle a path. Contradiction, suppose that this is non-zero. We can find an index k, where this is non-zero. Yes, this is essentially the idea. Okay, so let, we'll do A prime, B prime, and C prime, and say A prime is the average between B plus C over 2, B prime is average of A plus C over 2, and C prime is the average of A plus B over 2. By our we can also make another note up here. Yes, okay, so we could also do this. This is probably fine. Okay, yes, this is prime. This is fine. Okay, so okay. I'll edit this later. Okay, so I've just sort of added a little note here. So we're going to define a reverse-oriented contour. So if you have a contour, we can sort of mirror its direction. I'm using the superscript sort of fancy-looking M to indicate sort of a mirror direction. So if we have a contour, we can use the superscript M to form a different contour, where if we evaluate this new mirrored contour at t, it just sort of reverses the direction, does 1 minus t of the original function. This also means if we take the derivative of the mirrored direction, it's just the negative of the mirrored derivative. Also, if you have a concatenation and you mirror that concatenated curve, it's the same as concatenating the mirrored curves in the reverse orientation. So these are all useful. So I can also put this up here. Okay, so eventually I'll have to come back to all these properties I'm listing and prove them or something. There's a lot of them. Okay. Okay, so we've got A prime, B prime, C prime. That's these halfway points. We can say that, actually, instead of doing A prime, B prime, C prime, we can do, what's some other good letters for variables that's not A, B, C, or X, Y, Z? To A, to A prime, then A prime, actually not A prime, it'd be A to C prime, Greek. Yeah, actually that might help. Oh, but I can't use gamma. I'm already using gamma for contours. I'll do it anyway. No, I don't want to. I won't. I refuse. I'll figure it out later. Maybe we'll do it later. I'm also going to draw a diagram for S, so that I can visualize this more easily. What we're doing. I hope you appreciate my MS Paint skills. Okay, so we've got A, B, C, and A prime is opposite, and B prime is opposite, and C prime is opposite. And we want to do different loops. So the whole curve goes around in, yeah, so the whole curve goes around in this direction. Then we want to consider these sort of inner curves. This one will go around in this direction. This one will go around in this direction. Oops. And this one will go around in this direction. But this inner one will go around in the opposite direction. I think like this. So the idea is that when we add all these up, the integrals along these triangles, we'll just get the full outer triangle. So the outermost triangle is, so let's sort of put this over here somewhere. I'm going to post this beautiful image in the Discord, actually. So you can take a look at it if you need it. Okay, so what we're going to do, so we've got A prime, B prime, C prime. We're going to do these different, so we know delta is A to B to C. We want, we're going to do 4 different triangles. So do delta 0 is A prime to B prime to C prime. I'll fix these up with like actual line segments later. And so the inner triangle is delta 0. Delta 1 is A to C prime to B prime. And delta 2 is the bottom right triangle, which is C prime to B to A prime. And the last one, delta 3, is the bottom left triangle, which is, I think I actually don't want that to start from B prime. I think I want that to start from A prime. So I'm gonna erase this arrow. And it technically doesn't really matter, actually. I'll do it around at this direction. This one's coming from there, this one's coming from there, and this one is coming from there. All we've done is just rearranged which one is first. It actually really doesn't matter because it is a loop integral. But I've just sort of moved the starting point from B prime to A prime. Same contour. Okay, there we go. So that's the diagram we're using to help us do this. So we have delta 3 is A prime to C to B prime. And so we'll sort of fix these up. So we just have these sort of points here, A prime, B prime, C prime. So this is going to be this triangular path. Formally what we want to do is kind of concatenate these with line segments. I think that's actually pretty cumbersome. So instead what we're going to do is we're just going to sort of make this implicit. So we're just going to write this as an ordered pair. We'll just use a capital T. T, ABC. So T is triangle. So triangle, ABC, triangular path. That'll help us up in this segment. So we'll do T, A prime, B prime, C prime, and T, delta 1 is T, AC, B prime, and delta 2 is triangle C prime, B, A prime, and delta 3 is triangle from A prime to C to B prime. Let me make sure I've done that. Yes, I think that's all correct. Okay, so actually want to do A to C prime, and then C prime to B, and A to B. So if you do this summation, that equals 0 to 3. The integral of delta sub I f of x dx, this is just the integral on the original delta triangle f of x dx. So essentially, what we're doing, as in the diagram, if we add up the integrals on all four triangles, so we'll get the segment from A to C from the first triangle, A to C prime, from the first triangle, then C prime to B from the second triangle, B to A prime from the second triangle, and then A prime to C from the third triangle, and then C to B prime from the third triangle, and then B prime to A from the first triangle. So that gives us the full outer loop, just from the outer three triangles. But the outer three triangles also give us these inner lines. Sort of the key is that, though, like the first, for example, the first triangle follows that middle edge from C prime to B prime, but the middle triangle follows that edge from B prime to C prime, which is in the reverse direction. Since we go in the reverse direction, they cancel out. We could work this out on paper if we would like. But that's sort of the idea. We just want to use these properties of integration. So if you follow the path in the reverse direction, it negates the integral. That's this one. And if you concatenate different paths, it's the same as just summing up the integrals. These two properties are that's really the key importance here. That's how we would prove this equality. So it's kind of straightforward. So once we have this, so given this, we can find I in this set of 0, 1, 2, 3, such that, and so we can say this piece of k of this integral, this whole thing, is greater than or equal to a fourth of the original integral, the piece of k of the original integral. So something like this. So essentially, we're saying A, B, C, and S, triangular path. By contradiction, suppose that this integral is non-zero. Define the least index k for which this integral is not zero. Now we construct a second smaller triangle, and say actually we pick out these triangles, blah blah blah. Okay, so we end up with this. I might want to, maybe instead of doing capital delta sub I on these, we can do we'll say the other edges. Instead of labeling these capital delta, let's label them lowercase delta. Okay, that's nice. Hello! Welcome to the stream. Okay, so we're using these subtriangles. Okay, so you cut them up into subtriangles, so you can find some I so that this delta little triangle has this relationship. So, so we're saying, so since the length of a line segment is just absolute difference between their endpoints, okay, so this this new triangle that we've selected, so we've cut up our triangle into 4 subtriangles, and we found one of the 4 subtriangles which sort of maximizes, or at the very least makes this integral along that triangle greater than or equal to a fourth of this on this projection of the original triangular integral. And that's because we've summed up 4 things to equal this thing, and so of course on any projection we should have one of them being greater than or equal to the average value. So this will be greater than or equal to a fourth of this projection, so we'll label this triangle delta 1. So since we generally have the length of a line segment as just the absolute difference between their endpoints, it follows that the length of this new triangle is just a half the length of the original triangle. We should also have the diameters in terms of the A function this new triangle. This is going to be equal to the diameter of the original function, half the diameter of the original function. That's nice. Okay. So we label this triangle delta I is capital delta 1. We generally have this length is this absolute difference, so it follows that the length of this delta 1, this new triangle, is half the length of the old one. Also, the diameter of this new triangle is half the diameter of the old one, since they're actually just similar triangles with half the size. but actually, no, sorry, not these. We should have not the length on. No, this is correct. This is correct. That the lengths have this relationship, but this projection has this fourth relationship. That's fine. Okay, so the lengths have these relationships. The diameter have these relationships. Let's do this as xy. Oops, okay. Okay, so we've constructed this triangle and it has these properties. So the length goes down by a factor of half. The diameter goes down by a factor of half. The new triangle is subset to the convex hull of the previous one. And we have this inequality on the k projection, specifically k. It doesn't work for all of the projections necessarily, but it does work for the k projections. So we've selected this k projection in advance so that this integral is non-zero. But we've sort of done this. So so we've constructed this method. So let delta 0 be delta, and use the above method in an induction above method in an induction to construct delta sub n cross n in non-negative integers with the above properties, namely we should have the length of delta n is 2 power negative n of the length of delta, and the diameter of delta n is 2 power negative n of the diameter of delta, or we do delta 0. And for every n, delta m is subset to convex hull of delta, we should do n plus 1. Delta n plus 1 is subset to the convex hull of delta n. And the important part, so this integral, p sub k integral on this delta n triangle that we found, the subtriangle. So what we've shown, to recap, we start with a triangle where the integral is non-zero. That's capital delta. We find an index k where the projection of that integral is non-zero. So if it's non-zero, if the integral is non-zero, then one of its projections is non-zero. We cut this up into 4 subtriangles using these lowercase deltas. And we just observe that if we sum up the integrals on these 4 triangles, that this is just the integral on the original triangle. So we find one of these 4 such that its projection on p sub k is at least as big as a fourth, right? At least as big as the average of the projections, which is just this original integral divided by 4. And we can just label this triangle, whatever this I is, which has this inequality, we just label this delta 1. So we started with delta, we produced delta 1, and what we sort of observe is that by construction, since we always have this length as just the absolute value of the absolute difference, it follows that the length of this new triangle is half the length of the old one, the diameter is half the old one, and the new triangle is also subset to the convex hull of the old one. So we just repeat this process in an induction. So we get an infinite sequence of triangles labeled delta sub n. So each triangle has the above properties relative to the previous ones. So those properties are: the length is 2 power negative n of the previous length, the diameter is 2 power n of the original diameter, and also each successive triangle is subset to this convex hull of the previous one. And most importantly, that we have this inductive inequality. The projection of this nth integral is greater than or equal to 4 power negative n of this integral here. Now, using this, we can just exploit differentiability to show that this is impossible. So we can say let x0 be the limit point. Actually, so we can say since the convex hull of delta is subset equal to S is a compact set, we can find x0 to be the limit point, or rather a limit point. It is unique, but we don't really need to know that. A limit point of the images of all delta sub n as n goes to infinity. So we've got this x0 to be a limit point of these images. Actually, I think no, yeah, okay. So that's fine. So we have this limit point on the images. We should have x0 in the convex hull of every delta n. Actually, we can let x0 be okay, so we let x0 be the limit point. Then we can just say for each, actually, yeah, for each, let me think. So we have these triangles. I think what we want to do is say okay, so we can say actually, yeah, that's what we want. Subtract f of x 0. Okay, so this projection, if we just subtract, so we can just subtract, so we're going to do, starting from this inequality, we're going to say, since our delta n is a closed loop, and constant functions have an antiderivative, that means they have a path-independent integral. So this integration up here, we can actually just plug in f of x0 in this integral, and it doesn't change the value at all, since the integral is on a closed loop. So if we just subtract f of x0 over on this left side, we can also do this, this inequality here. So let's label this integral for convenience. Blah, blah, blah. Okay, so we cut up these triangles. Okay, etc., etc. Okay, so I've just labeled this, the original integral, as I, so that's a little easier. Okay, that's good. So you're back here. So we can say find y sub n in the image of delta n such that y sub n and delta n such that we have, that should be uppercase I. There we go. So this projection is less than or equal to, we have p sub k of, let's see, we have length of delta sub n times f of x minus f of x0. And this is for any x in delta sub n. Oh, I messed that up. Okay, there we go. Actually, we can just rearrange this. That, which is this should be on the right side. Okay, better. This length of delta n is just the length of delta times 2 power minus n. Okay, so we're looking at so this is that. So for n, yeah, okay. This is bounded by that, which is bounded by this pk of this length delta n. But this is just 2 power negative n, p sub k, length delta, absolute difference, f of x minus f of x 0. Let me think here. Oh, sorry, this should be not less than or equal to this. This should be let's pull off these. Okay, since f is continuous and delta s of n is compact, we can select y sub n and delta n to maximize, or rather actually we can just say okay, so this integral, this should be absolute value. I'm a silly goose. This integral isn't greater than or equal to, it should be absolute value. Okay, that's better. Okay, so we have this absolute value this, less than or equal to absolute value of this. But this is just What do I want to do? We're trying to find y sub n to maximize this integral. Okay, so what we want to say is this projection of this integral, this is bounded by we have absolute value of the length of delta n times, this should be beta, which is okay, I've got it. Let b beta be the least upper bound for f of x minus f of x0 over x in the convex hull of delta, which is possible to find since f is continuous and delta is compact. Actually, I should say the convex hull of delta is compact. Okay, so now that we have this bound, so what we can do actually is say oh gosh. The idea is to select x as some y sub n to make this difference really large. Now we have, okay, so okay, so this is less than or equal to, we have this projection less than or equal to this times beta, which is 2 power negative n, pk, length delta, and then this here is beta again. Okay. And this gives us piece of k I, as a value piece of k I is less than or equal to, multiplying by 4 to the n, we get 2 power minus n, or sorry, 2 power n of piece of k length of delta times beta. Oh, capital B. Okay. I think this is what we want. Nope, this doesn't help us. Actually, okay. Okay, this works a little better. Okay, so let beta sub n be the least upper bound for f of x minus f of x0 minus x f prime x0 over x in do delta sub n. Okay, so now we have this relationship. Okay. And list these are beta sub n's. Okay, this is fine. Okay, so what we're doing now is we are subtracting off. So we found all these triangles and so on with these relationships. We found the limit point of these triangles. So these triangles are limiting to a point. And all of these integrals have this earlier inequality. What we've done is, since f is differentiable, we can find its sort of linear, its sort of tangent line, basically, at this limit point x0. So using the differentiability of f, we let g of x be that linear function. Every linear function has an antiderivative. You can just use the polynomial antiderivative. It's super straightforward. So this function has an antiderivative, and we know that if a function has an antiderivative, it has an indefinite integral or a path-independent integral. So from this we have, since delta sub n is a loop, this integral of g is 0 for any n. That means that we can just sort of shove this g of x in this integration. And it's exactly the same inequality we had before, but we've just put g of x in here. Now we can say we can bound this integral using the length of delta sub n. So let beta sub n be the least upper bound for this difference. So f of x minus g of x over x in delta n. So this is possible to find since f and g are continuous and their domain delta sub n is compact. The continuous image of a compact set is a compact set, and we know that any compact set has a least upper bound in its absolute value. So we let beta sub n be that least upper bound. And then we can plug this into here. So using that, we have this projection, this integral. This is just bounded by, right, we have the length of the curve, which is delta sub n, times beta sub n, which is equal to 2 power negative n times this thing. What that actually means is that we have this inequality right here. So we actually have this kind of expression. Yes, so this, we have some constant, which is our original integral, times 2 to the power of negative n. This is that, this one, by just multiplying through by our 2 power negative n. This is less than or equal to this length. However, again, since, and actually we want to say, let me think here real quick. So we want to do, doing this bound, this is less than or equal to that, which is less than or equal to that. So we want to do, we can select some y sub n to maximize this. So since our beta sub n is sort of our least upper bound, essentially, so we have this inequality, length, bk, so on and so forth. Okay, so since we have since f is okay, yeah, differentiable at x0 for any sequence of y sub n going to x0, we must have this fraction f of y minus f of y sub n minus f of x0 over y minus x0. I'm going to f prime, and actually if we subtract minus f prime of x0 going to 0, now essentially we just want to pull this approximation out. So normally the way that this is done, we can look at this. Normally the way that this is done, we have this maximum m is the, let's see, this is the original Cauchy-Gauss set. M is our original integral, I think. Yeah, m is the original integral. We've shown that each of these integrals are greater than m over 4 power n. And then, okay, so okay, so we can say okay, so we have this thing. Oh gosh. Because I also have the original version somewhere. We've got a really interesting one, actually, in this original version. Oh, that's what I did. Okay. We can bound the distance between, the absolute difference between 2 points that are in the convex hull of delta sub n. We can bound it actually by the length, just the perimeter of delta sub n, which is just the length of the original triangle times 2 power n minus n. Actually, that is what we can do. Okay. I actually did one of these parts wrong. We should have, G should be, I just did x times f prime. It should be x times x minus x is 0. I think maybe that's what was tripping me up. Yeah, so that makes more sense. So that's what we've got. So we're bounding this with this times this absolute beta sub n. If we do this projection on, right, so this applies for the projection on K, which is what we have. And so next we're trying to say, Okay, what happened here actually? Right, I think that's what's getting me. So, okay, so what I'm getting confused, so I've got this projection piece of k on this length of delta, times this beta sub n. This beta sub n might not be so super useful. I think that's what is getting me confused. Or sorry, it is useful, we need it. But because we have this projection, our beta sub n is not guaranteed to be is not guaranteed to be a real value of any sort. So I think what we want to do is, at this stage, we want to use differentiability to show that the magnitude of this has to drop rather fast. So what we'll say is, so what we've shown is that this integral, or rather, this integral is bounded below by this expression. What we want to show is that it's actually bounded above by that expression as well, strictly, that it tends to 0. Okay, so yeah, and that's the problem with this part here. I know why. So first of all, I've lost these absolute value bars for the 11th time. We need to do the submultiplicativity. So we have this absolute value of this, bounded by that, absolute value of that, bounded by this, which is equal to this expression here, and then this projection, this should be an absolute value. So this should be absolute value piece of k and then this is okay, let's do that the other way. Okay, so okay, let me think. Let's multiply this 4 power n through, perhaps. Yes. No. Okay. So we should also have f of x minus g of x if we divide this by x minus x 0, this should go to 0, and in fact, yes, that's correct. So this should go to 0 as x goes to x 0. Right. What we want to try to say is that this this expression is, if we take this expression and we multiply it by 2 to the power of n, okay, yes, so, oopsies, oh gosh, lost my place. We're up here. Okay, so the diameter of delta n is equal to 2 power negative n, the diameter of delta, then we should have actually a of x minus x 0 as being bounded by 2 power minus n, diameter delta for any x in delta n, the nth triangle. Okay, let's give it some space so I can see what we're looking at. So we're right here right now at the moment. So by differentiability, this differential quotient goes to 0 as x goes to x naught. Since the diameter is 2 power n times the diameter of delta, we should have this absolute difference bounded by 2 power n times the diameter of delta. Yes, for any x in delta sub n. So it follows that this thing, if we multiply this by so this a of f of x minus g of x, this is just a of this fraction times x minus x 0, and we're going to have to just put this on its own line, and this is bounded by so we have a of this difference quotient times a of x minus x 0 by x minus x 0. The a of that is bounded by this. Two power negative n times the diameter of delta. We know this term goes to 0. That's nice. And that's actually probably good enough. Okay, so now we can say for each n, let beta be the supremum of beta sub n, be the supremum of these difference quotients across x in delta sub n, so that as n goes to, actually we can just say so that beta sub n goes to 0. So that's useful. But then, so we bounded this integrand. Now we have this up here. P sub k, integral on delta n. This is less than or equal to, right, so we have the p sub k of the a of the integral. This is bounded by, so we have the length of delta sub n times the upper bound of this difference, f of x minus g of x. And we've just shown that that's bounded by beta sub n 2 to the minus n times the diameter of delta. May have lost some parentheses there. Right, so this integral we have, this is bounded by like delta times that, but this is just our length of delta there. Length of delta n is just 2 power negative n times that, so we can pull this 4 power n to the front. Okay. Let's put all these inside a line environment. A line there and there. Okay, and let's also rearrange. I want the diameter next to the lengths so that those are constants with n. Okay, great. Actually, that's excellent. Because our other flies. Okay, so our other expressions, so we had this, and now we have this. Actually, and that gives us this final expression. expression here. And we can cancel out these 4 power n's. And I think we're done. Actually, that's it. It's very messy, but this should work. It's very messy. Okay, so the way we're going to do this is we pick our triangle as this triangle from A to B to C, fix an index k in naturals, subdivide the triangle into 4 subtriangles, as in our diagram, use the properties of integration just from concatenation to show that this sum of these integrals is just this final integral. Then we can just find some I in 0, 1, 2, 3, one of these triangles, where the absolute value of this projection is greater than or equal to a fourth. So because this is equal to, this sum of these 4 things is equal to this final thing, their average is a fourth of that, and we should be able to find one of these 4 things which is greater than or equal to the average. So we label this triangle as delta 1. Note that delta 1 is similar to delta with scale factor of 2, so if this length is half as much, diameter is half as much, and the new triangle is subset to the convex hull of the previous one. So delta 1 is a subset to, yes. So label delta 0 as delta, our original triangle, and we use the above method in an induction to construct these series of triangles with the above properties. So the length goes down by a factor of 2 every time, as does the diameter, and also each successive triangle is subset to the convex hull of the previous one, and such that we have and such that we have this integral of each of these delta n triangles as greater than or equal to 4 power n. So since our convex hull is a complex set which is subset to S, we find a limit point. We should have x0 in the convex hull of delta n for every n. Using differentiability, we find g to be this linear approximation. This has an antiderivative. It's just a polynomial. It has a simple antiderivative, which means its integral along a closed loop is 0. So when we sum these, so we can just put this in this integral and it doesn't change the value. By differentiability, though, we also have f of x minus g of x divided by x minus 0. This is tending to, this should be, actually we can write this out explicitly just to be clear. This is equal to f of x minus f of x 0 over x minus x 0, and also minus f prime of x 0, and this goes to 0 as x goes to x naught, because this is just the derivative minus its actual, this is the difference quotient, the limit of the difference quotient, which is the derivative minus the derivative itself, which goes to 0. Since this diameter is 2 power n times this diameter here, we should have this absolute difference between any x and x0 for x in delta n. So we should say across x in delta sub n, we should have this inequality. So then we've bounded these x minus x zeros. So it follows that if we take this absolute difference of f of x minus g of x, this is the same as we have this difference quotient times x minus x zero, and then we just bound this with, you know, x minus x zero is bounded by this, which is here, and then we just have this absolute value of this. For each n, we can let, actually, let's do this earlier. We'll say, we'll say let beta sub n right up here. So we've noted that this difference quotient goes to 0. Let beta sub n be the supremum of these terms across n in delta sub n, so that beta sub n goes to 0. So that's what we want to do. We've done that earlier. And then since we have this diameter across x and delta n, we have this difference. So, and then we have the absolute difference of f of x minus g of x. This is just this product. This is bounded by the difference quotient, is bounded by beta here, beta sub n. Right? And then we have the difference of x minus x zero is bounded by 2 power n diameter sub n. Just diameter, actually, diameter of delta. Then we can sort of close this out. So this gives us, so we have this, this absolute value, this original integral. This is bounded by this projection. We have the length of delta n times this bound, beta n, 2 power minus n, diameter delta. This is just, we pull out these powers of 2 power n. We have 4 power negative n, length of delta, diameter of delta, beta sub n. So we have equivalently, we can put this earlier and say there we go. So now we have this original lower bound to our integral on our triangles is bounded by this expression that we just did from this, and the triangle inequality for, or the bound for an integral using the length of the path. This expression is just this, but then the consequence of this is that if we multiply by 4 power n, this p sub k of I is bounded by this p sub k of the length of delta times the diameter of delta times beta sub n, which we know goes to 0. And that's it. So we therefore conclude that p sub k of I is 0, since k in natural was an arbitrary index. Since k was an arbitrary index, it must be the case that I equals 0, which was the claim. And I can restate that. Integral on delta f of x dx is 0. And that's it. That's the that is our first proof. It's not too terrible, to be honest. Great. So, so as a recap, we've essentially proven, so if we have a convex set and a differentiable function, then that differentiable function has a vanishing integral over a triangular path. So that's nice. And so essentially, the way we've proven that is we've taken the triangle, split it up into a bunch of sub-triangles, picked the biggest one, the triangle that makes the integral the biggest, found a limit point, and then shown using differentiability that the and all of our estimations on integration, using like the length of the path and so on, that has to go to 0 very fast. In fact, the difference between f of x and f of x0 has to tend to 0 faster than linear decay. If we subtract the derivative linear term, that has to decay to 0 faster than linear decay because we have subtracted off the linear component, and that's why we get the 0 derivative, or the 0 integral. So that's nice. So that's our, that's that. So the next theorem we can go for, let me check how long we've been going on for. Yeah, let's try to do one more. I think the next one will be a lot easier than this one. So the next proof that we want to try to do is maybe which part? Oh yeah, I've reworded this so that there is not, we're not doing this by contradiction. It's straightforward now. Originally it was going to be doing by contradiction, but we ended up not needing the assumption that would require that basically anywhere. Yes, probably. You are correct. Let's see. This one is not suitably justified. Yeah, there's lots of little bits and pieces that could use some filling in. It would be much a longer proof if we filled in all the bits and pieces for sure. This one and all of these are fine actually. These are justified by, as long as the previous one is fine. No, this one is fine actually. So this follows from essentially the previous observations. This one is okay. So all we're doing is we're connecting. So we've made this original estimation. So all these triangles are set up so that they have this property, and then we use differentiability to show that actually they also have this property here, and then we just combine these estimations. We could probably separate these on something like, take this off this side and take this here. That ampersand is not supposed to be there. Let me try to space this out. Okay, I'll fix the wording later. There's a lot of edits just to the phrasing and wording that we can work on. But just having sort of the essential proof here is really what we want for now. Yeah, so let's attempt to do this next one though. So this next proof is, it's still a convex domain, and we still have a differentiable function, but instead of just having triangular paths, we're going to find an indefinite integral function, just overall. So to show that f has an indefinite integral function, it's enough to prove that f has a vanishing integral on any closed loop. So if we get this, then that basically means that any two paths we take between points will be 0. So as we note, that this is already true for triangular paths from the previous theorem, and the triangular case enables us to prove it inductively for any polygonal loop. To prove it for the general contour, so maybe we'll do a proof for the polygonal case later. Or like in an appendix or something. But we'll just advance on to the general case. We'll assume the polygonal loop case. And we'll prove it for a general contour. We just approximate this path using polygonal loops. And show that the convergence is justified. So to do that, so let f be, or rather, let sigma subset equal to S be a contour. Then for each n in natural, we construct a polygonal loop. We'll call this P sub n by concatenating line segments between the points. Actually, we can just call this, let's say, P sub n of t is equal to, we'll have it's basically going to be a line from some point A to B. These points will be sigma something else. Between the points sigma 0, sigma 1 over n up to 2 over n all the way up to sigma 1. So I do want an explicit formula for this. So for each t, we'll do p of t. I'll just do this temporarily. Is the floor of t times n. This is the portion it's on, and then if we're on that portion, we do x of t is p of t. Sorry, it should be nt minus p of t, and then we have n is just this line segment. We have sigma of p of t over n. Actually, we do over n there. No, this is fine. Okay, so p of t over n plus we have something minus something else times sigma p of t plus 1 over n. Something to this effect. Okay. Actually, it should be sigma minus, it should be the difference. Times this term here, which I think is x of t. Or equivalently, let's do r of nt. Okay, so we have think this proof is not going to be too difficult. Essentially, actually, because f is differentiable, it's continuous. And these polygonal paths, the value of f on these paths should actually converge uniformly, I think. I think so. I'm not sure, but we will find out. Okay, so we have blah blah. Okay, I think that is what we want. Let's rearrange these. So we have r of nt times that, so minus this times 1 minus r of nt. And we can get rid of this and that. I think that is good. Okay. Okay. So we've constructed our polygonal path, and essentially we're just sort of naturally connecting all these points, sigma 0, sigma 1 over n, sigma 2 over n, and so on. We're doing it in this really particular way. We're making it so that these, we're actually making it so that p sub n, its parametrization also approximates sigma. So not just its image, but its parametrization. Okay, so we've set up our approximations, and we've made the observation that since all of these are polygonal paths, the integral on these polygonal paths is independent. So if you take f of x, this integral of p sub n, this is just this integral. This is this line integral. Oh, we should actually make this note. Okay. Okay, so we've got this path. This path stays in S because it's a polygonal path, and S is convex. We have since we have path-independent integrals over polygonal paths, then this integral on p sub n is this, which is just 0. Follow since p sub n 0 is p sub n of 1. So we just have this straight line path, which covers no distance. Now using the substitution rule, we have this integral on sigma fx dx. This is just the integral from 0 to 1 of f of sigma of t, sigma prime t dt. And similarly, we also have, if we do this integral on p sub n, then this will be exactly the same expression, but with p sub n. Now all we want to do is show that all of these terms converge quickly in some sense. So since f is continuous, Okay, so actually we should say notice that as n goes to infinity, we have p sub n of t going to sigma of t. And since f is continuous, we have f of p sub n of t going to f of sigma of t pointwise. We should also say actually we can do a projection if we want. So we're going to have to work around the fact that sigma is only piecewise differentiable on each of its projections. Okay, so we're saying as n goes to infinity, we have p sub n of t going to sigma t pointwise. And since f is continuous, then we also have f of p sub n going to f of sigma pointwise. Moreover, if we union all the images of our p sub n polygonal paths along with the image of sigma, that should be sequentially compact, and therefore compact. In fact, well, we know it's going to be bounded, and it'll also be closed. Closed and bounded means compact, so this is a compact set. By continuity, it also follows that f of p sub n of t, that's bounded across all n and t. So we have f is converging pointwise, and it's bounded across all of the n and t's. In order to apply a dominated convergence, we also need p sub n prime. We need this to converge pointwise and to be bounded as well. I think that is something we can do. So we know that sigma is piecewise. Okay, yes. So we know that sigma is piecewise differentiable on each projection. Oh, I shouldn't use p here because we're already using p for something else. Let me use a different symbol. Shouldn't be p. We'll do gamma, because why not? Or actually, you can go a step further. Just call them all sigma sub n. They are approximating sigma after all. Okay, so we're going to show that right-hand integral converges pointwise to f sigma t sigma prime t, and that it is bounded n and t. Okay, so we fixed that a little bit. I've labeled the path sigma as sigma infinity, since all of our sigma n's are limiting there. That seems to make sense. So we have all these polygonal paths. They all have this zero integral, and we're going to show basically dominated convergence. So we're going to show that the right-hand integral converges pointwise to, okay, so to f sigma infinity, sigma prime infinity, and that it is bounded across all n and t. So first we notice that as n goes to infinity, so they do converge pointwise. And since f is continuous, we also have f converging pointwise. Moreover, if we union all the images of the sigma n, we should have a compact set, so continuity implies that this is bounded. So now we need only prove the same condition over sigma prime, sigma sum n prime. So f of sigma, if sigma nt is limiting pointwise and bounded, and so we have to prove the same thing for the sigma n primes. So to do that, we'll have to show that it is bounded and convergent. So to do that, we'll say call that for each index k in n, we must have p sub k of sigma of t as being piecewise differentiable. As being piecewise differentiable for each index k. Moreover, if we compose p sub k with sigma sub n, we get, so if we just apply this projection onto the sigma sub n, we're just going to get, not that one, also not that one, this one. Okay, so we do p sub k, so the k projection of sigma n t. This is p sub k of, actually we can just do this here, and then plus this other thing, p sub k, all these things, right, parentheses. Okay, so we're basically just noting, just by the definition, if we do this projection on this polygonal path, sigma sub n, this is just all of these other terms, this is real, so this projection is just ends up on these sigmas. So actually this polygonal approximation, sigma sub n, this is actually the polygonal approximation of sigma. If we do the projection, it's the same as the projection of the, the projection of the polygonal approximation is the same as the polygonal approximation of the projection. So the p sub k projection of the approximation is a polygonal approximation for the projection, and since it is a piecewise differentiable continuous function on a compact domain 0, 1, it follows that we should have p sub k of sigma sub n of t converges to p sub k sigma, actually it's piecewise continuously differentiable. Follows that p sub k sigma n t converges to p sub k sigma t pointwise and with and by, actually want to say so this converges pointwise, and we should have also be bounded. So since we have our projections bounding and converging on every index, it follows that p sub k, actually just sigma sub n of t prime goes to sigma prime of t. Let me be more precise. So p equals blah blah blah. Polygonal approximation has d dt, same, converges to d dt, the same, pointwise. And bounded across all t. The real derivative permeates with our projections. Follows that p sub k sigma n prime t converges to p sub k sigma prime t pointwise and while being bounded on across all n and t. Okay, let's take a look at that. Should be, there we go. Okay, so finally we have f of sigma sum n of t times sigma prime of t to converging to sigma sub n prime, converging to f of sigma t sigma prime t pointwise and dominated by some constant across all n t. So by domain convergence theorem, we have the result, which is that the integral on sigma sub n, so we have 0 is the integral of sigma sub n f of x dx we could do integral on sigma fx dx. This is integral on 0 to 1 f of x dx, which is, sorry, f of sigma t sigma prime t dt. This is the limit and goes to infinity. Same integral of sigma sub n, which is just the limit of this integral sigma n, which is just 0. Awesome. Okay. So that's nice. So we've sort of offloaded a lot of the difficult part of using this path to a sort of a real analysis problem. And we're just saying if you have a piecewise continuously differentiable curve, this expression will limit pointwise and be bounded. That should follow from intermediate value theorem, actually. So our function is piecewise continuously differentiable, so intermediate value theorem, or sorry, is it mean value theorem, guarantees that these average slopes will each of these average slopes will be in the image of sigma prime, which is bounded. The derivative of our polygonal approximation is actually in they're all just secant lines, essentially. And all of those secant lines, their derivatives are just some constants that are in the image of the derivative, sigma prime. So it should be bounded. It should be converging pointwise, because we're just taking, polygonal paths, polygonal approximations that should converge. The derivatives should converge pointwise anywhere that it's differentiable. And we essentially just offload that problem. Since this applies on applies on every index, it'll also apply for the functions in general. So our substituted integrands converge to what we want them to pointwise, but all of these polygonal paths are just 0 integral. So our final integral is equal to this substitution, which is this limit of these integrals for the polygonal paths, but each one of these is 0, and that is the solution. And we're done. That's nice. So that's that proof, which is we've shown that for a convex domain and a differentiable function, there's an indefinite integral function for f. Technically, we haven't shown there is an indefinite integral function for f. We've only shown that integrals on loops vanish. We could be more precise about that. We could say let S be subset A be convex, F be differentiable, then the integral of f on a closed loop vanishes. So that saves a little bit of exposition. So this is already true for triangular paths by the previous theorem, and the triangle case enables us to prove it inductively for any polygonal loop. Prove for a general contour, we just approximate using polygonal loops. Okay, awesome. So the next thing that we want to do is we want to, the last sort of piece is showing that instead of just having a convex domain, which is what we have here, we actually want to do it for any locally convex simply connected domain. Okay, so I think we don't have enough time to prove this today. It's not a super complicated process. However, the essential idea is because we're in a simply connected space, and I can draw a diagram here. Given any closed loop contour, essentially we want to find a homotopy. So a homotopy is a function, so we start up here with our curve, our loop sigma, up on this. So this is our domain is of the homotopy, a function rather, f s t, where s and t are in 0, 1. So the domain of a homotopy is a unit square. It's such that if we have, so this will be our t-axis, this will be our s-axis. It's such that at the, when s is 0, we just have this sigma path. And in order to do, because it's simply connected, we have a homotopy to a point. So down here on this bottom portion, it'll just be flat x0. On the left and right side, since we have, or sorry, not x0, yeah, x0, which is sigma of 0. On the left and right side, we also have x0, because it's just sigma, on the right side it's sigma 1, and the left side it's sigma 0, which is all just x0. So this left and right side will all be constant. And we can actually label these axes down here. So it's the t-axis, it's the s-axis. Essentially what we're going to do, this is sort of the proof sketch, is we're going to take this homotopy sort of grid, the domain, and we're going to cut it up into really fine pieces, sort of like this. And we're going to find a way to cut it up into really small pieces. So we'll cut it up like this, and we'll also have it cut up like this as well. This is sort of our idea for how we're going to prove this. So we're going to try to find a sufficiently small, amount to cut this into pieces like this. And we're going to do it in such a way that the image of this homotopy across one of these little square pieces of the grid, that the image of this homotopy on this square is stuck inside a convex subset of the domain, capital S. Once we do that, we can just use the path independence of for integrals on a convex set, you can use that property to show that an integral on this little square is going to be 0. And then we just add up all of the squares, and it just so happens that they all cancel out in such a way that this integral on this top loop is the same as the integral on this bottom loop. But the integral on the bottom loop, the value of the loop is just a constant, and that has no length. A constant loop has no length, so the integral is 0. That's sort of the proof sketch that we're going for, or that we will be going for, but not right now. Right now, I think we have gone on for long enough today, but this is what we will be doing next time. We'll be proving this, this proof. So we will show that for any locally convex, simply connected domain, a differentiable function has a path-independent integral. So its integral over a closed loop will vanish. Yes. Thank you for joining me today. I hope you learned something. If you have any questions, I can answer them right now, actually, before we head out for the next couple minutes. If you'd like to look at any of these again, or get some ideas on them. Was I led by natural next steps, or did I have to figure stuff out specifically? Definitely, it was not natural. It seems really sort of natural with the way that's being presented now. And that is because I've been working on this draft sort of on and off for like, I think a year by now, a year and a half. So it definitely seems a little more natural than it actually is. This, for example, this proof for the triangular paths, yeah, it was very difficult, in fact, to be completely honest. A lot of the things came naturally, but a lot of them didn't. Yeah, that's good. I'm glad that it seems natural. Obviously, not all the proofs are super fast. Like, some of the proofs are a page long or so. But they're much shorter than they used to be. I can pull out my original draft. I mean, you can actually just by looking at it, just by looking at the original draft. So right here we're down at considering all the integration stuff. We got through power series in 21 pages through everything. I'm assuming this last theorem for integration is probably only going to take a page or so more. So like in about 20 pages we've gotten through power series. In my original draft, it took me so long. We were at page 37 before even starting power series. If that gives sort of an indication of how much it's been improved. Page 41 is how long my original draft took to get through all the same sections, same basic material, but just to get to the same point took about twice as long. So we're definitely, it's drastically improved. All of the stuff about, so for example, in the power series section, we've all these really nice characterizations for this phi function, and we have different theorems about how to apply it. In my original draft, I think I didn't even have a phi function. Yes, it is a nice densification. It's very nice. It's very nice. Yes. Yeah, so I'm very glad with how it's going. Of course, I'll have to probably edit the wording. I think actually I really don't want to touch the other sections, like differentiation, power series. I think those are pretty good in this version of the draft. I think they're pretty final. The integration section will have to be sort of spiffed up, but this too is a lot better. One of the interesting quirks, actually, a lot of these proofs are really hard to do. It's really hard to find them in this context because of, there's just so many degrees of freedom, and there's so many things that can go wrong. It's really hard to prove them that they actually work, or it's hard to find the right way to do it. So like, for example, even our current version, if you look at the derivatives section, other than like the last proof, which is very, very much about, you know, projections and being able to divide things, other than like this last proof, all these proofs, they're exactly the same proof you might see in like a Calc 1 class. But they had to be selected really carefully to make sure that they actually follow in this context. Especially because the division is really finicky, because you can't always divide things, even if it's non-zero. So all of these proofs had to be selected very carefully to make them actually work. In my original draft, I didn't even use this definition of derivative. In my original draft of my paper, where all of these theorems essentially came from, I originally used the definition, right around here. Nope, higher than that. Here it is. I originally defined the derivative using, so it was still the difference quotient, like you would expect. But instead of having one fixed point and then one free point that tends towards that fixed point, it was two free variables, which would tend to that point. So instead of having, you know, f of a minus f of x as divided by a minus x as a goes to x, it's f of a minus f of b divided by a minus b, as both a and b tend to x, but not being equal. Doing it this way essentially makes this definition of derivative was a lot stronger. For example, it implied continuous differentiability, which made a lot of things really easy. Also, sometimes there are some cases where just not needing, you know, both one of the variables to be fixed made it really easy to prove lots of conditions, especially when you get into like integrals. My original versions of the proofs for antiderivatives and indefinite integrals being the same thing, my original proofs required that this notion of differentiability, that both variables could sort of be free. And I spiffed that up quite a lot. The new proofs no longer required this strong of derivative. The original proof also didn't have this, what we have. We have essentially a Cauchy-Goursat theorem, which is that if you just have a differentiable function, not necessarily continuously differentiable, if you just have a differentiable function, then your function has a vanishing integral over any triangular path for a convex set. Also, differentiation used to not be framed in terms of convex sets. It used to be framed in terms of open sets, which is actually a really big restriction. The open sets in this context are really large. So there's lots of open sets, there's not very many open sets because they have infinitely many degrees of freedom. But because we've done it this way, using just convex sets, or convex sets without you know, convex sets without isolated points, or simply connected convex sets, because we've done it in this way, there's actually quite a lot. There's quite a lot more freedom, and I used to not know how to do any of that. So a lot of these proofs are new. This proof in particular, this one's new. This proof the proof that we just wrote, that in a convex set, the integral of a function over a differentiable function over a closed loop vanishes. This is the first time I ever wrote that proof. I've never written that proof before. I was pretty sure it was going to work out based on just the triangular case. But I just sort of came up with proof. I mean, you just watched me come up with a proof right now, and just sort of flesh it out. I think that's probably the real raw proof making experience I think that's been on stream so far. It's all pretty similar. I try not to look too much at the previous proofs and just do what I think will work. But this one, of course, this proof is, I think this one's a lot easier to sort of understand. So it wasn't as hard to come to as the other proofs. But yeah, the proofs, they did not come naturally. They look natural, but they didn't start out that way. So I think it's really nice. It's almost deceptive, actually. I presented these to Doran, and he was kind of, I guess he was sort of surprised, or maybe not surprised. The proofs are so straightforward that it almost makes it seem obvious, but it's really not obvious at all. It's not obvious. It's very, you have to be very careful with a lot of it. But it's nice. It's fun. Anyway, yeah, so thank you for joining me. As always, you can always ask questions in the Discord server. I'll always reply to them if you just happen to have a question or suggestion or anything like that. But thanks for joining me. I hope you have a nice rest of your day. Next time we'll come back probably tomorrow. We'll come back and do this proof. And then we get to attempt to get into the really fun stuff. Yes. Spoiler alert. If we have add some extra conditions on these domains, it turns out some differentiable functions end up being analytic. So we have that to look forward to. Okay, bye. Thanks for stopping by.